Hello, this is Veder Gaumans with Software for Chemistry and Materials. In this video I would like to discuss with you and demonstrate a few new capabilities in the 2020 release of the Amsterdam Modeling Suite. In this release, our flagship molecular DFT code ADF has been fully integrated with the central AMS driver, enabling you to do easier switching between ADF and the other modules, also easier to set up complex tasks on the potential energy surface. So we have our simple tasks here: geometry optimization, transition states, ISC, NEB, and so on. But if we want to do something a little bit more complicated, then in the graphical user interface on the top level on the model, you will find ways to define your system, followed by the complex potential energy surface tasks such as grand canonical, Monte Carlo, and molecular dynamics options. Below, always at the bottom, you will find specific options only to that method. So if we were to switch from ADF to DFTB, then under the model we'll see only options available for DFTB at the bottom. Same thing under properties, so these are the properties available for that particular method, and then below that those are specific properties available only to DFTB, or not only, but they are available to DFTB. So for instance, DOS would be available to band and ADF as well. We'll notice in the drop-down menu there are a few new engines available there. So first there's the machine learning potential, and the machine learning potential installs automatically after you give it consent when you first run this version, and it's a very quick and relatively accurate method to optimize organic molecules. So if we have a molecule like this, if we click show output, we can run it interactively. Let's choose this pre-parameterized model. You can plug in your own machine learned force fields as well via a number of different interfaces. And you will notice there's a little bit of startup time, but after that all the geometry optimizations are essentially instantaneously done, and it takes a few seconds just to run the optimization. So it took 8.08 seconds, but 8 seconds to initialize the machine learning potentials in this case. I invite you to watch a video by my colleague Matti to learn more about the thermodynamics and statistics involved in running these type of machine learning potentials. Another new module available is Hybrid, and Hybrid is our multi-layer method that allows you to do anything on the potential energy surface using a combination of different methods. So there's the classical QMMM additive type of calculation that is available only for a QM layer, ADF band or DFTB, and a force field layer for which we've introduced a new engine called force field, and that can be run using electrostatic embedding as well as mechanical embedding. More generic multi-layer approach is called energy terms, alternatively known as subtractive QMMM, Onium or Quilt as it used to be available in the Amsterdam Modeling Suite, that allows you to easily set up any number of layers that you're interested in by defining different energy terms. And that can also be used with any type of periodicity. So let me demonstrate that for a 2D system. So let's look at graphite. And from graphite we will slice one layer. So we have graphene. And we need to remove one of these. And let's generate a 4x4 supercell. Now let's say we're interested in the absorption of water onto graphene. Let's build water here. We can define a region here on the model region where we have water, and then if we go back to the main input panel, we want to calculate that at our highest level, let's say DFTB, and we want to calculate the remainder of our system using a force field, and then that force field can be defined here in our panel. Let's use UFF, and DF2B, let's use the standard GFNX2B. Now if we go back to the hybrid panel, then okay, we do a geometry optimization. We calculate the energy of H2O at DF2B. We add the energy of the entire system using the force field, and then we subtract the energy of water at the force field level. So we take kind of double counting. Let's save this as water graphene and run that calculation. Job run. And so this QMMM setup or subtractive QMMM can be used with any engine, and it can be used for any periodicity. So if we have a look at the optimization itself, good. So if we wanted to, we could also do a calculation with band under the water molecule and then use DF2B for the lower level. And then we would do a QM prime type of calculation. If we wanted to do another layer, that would also be possible. So you could have 3 layers, 4 layers with any periodicity. Okay, let's switch back to ADF and let's remove this water molecule here and then remove the edges of the PAH flake that we now have, because this is zero dimensional, and hydrogen atoms, and do a quick pre-optimization with the machine learning potentials of this flake of graphene. And again, it takes a couple of seconds to initialize, but then it should be pretty quick. You see 0.70 seconds for the actual geometry optimization. Now let's use this particular molecule, this pH, and use a new functionality in ADF, which is G0W0, which is giving access to more accurate ionization potentials and electron affinities based on cone-Charm orbitals and the quasi-particle approximation on top of that. Usually you'd want to use a hybrid as a starting point, so we can use PB0, and you'd want to use something like TZ2P as a basis set. So it's recommended that you use a good numerical quality, but then for the resolution of the identity Hartree Fock, we can get away with normal. Now if we save this as pH G0W0, we can run this calculation on a slightly bigger machine. We ignore this warning here, so frozen cores, probably it's better not to use frozen cores, but usually you can get away with it at a much faster calculation. And we put this in our remote machine and then run it there. Okay, so the job is finished. As you can see, it's taken about 13 minutes. If we have a look at the log file, we can see that the SCF itself took around 4 minutes, and then it's around double that time for the G0W0 part, and that's kind of the same. So G0W0 implementation by Arne Fuss is pretty fast, and it can be a pretty good method to predict ionization potentials and electron affinities. So let's have a look at the output file and search for G0W0. And let's scroll through this. There we go. So we can see that these are the cone-Charm energies of the highest occupied molecular orbital at -5. If we apply the G0W0 approximation on top of that, it will come down to -5.4, whereas for the lowest unoccupied molecular orbital, which is related to the electron affinity, it goes up from minus 2.8 to minus 1.1. In the meantime, I've been able to identify the nature of this PAH, which is called dibenzo BC-KL coronine. And then I found in one of the astrochemistry databases the ionization energy and the electron affinity. So 1.54 eV for the vertical one, 1.48, and that is to be compared to the calculated value of 1.16, and for the ionization potential 6, that is to be compared with minus 5.4. So it does improve, but it doesn't get you all the way there. And we're looking forward to further improvements to go to better GW approximations. And finally, I would like to discuss with the old ADF users the input structure. Let me go back to the input. And as I mentioned, it's been fully integrated with the central driver. That is reflected in the run script. So in the run script, you'll find now first the task. So what is the main task that the AMS driver needs to do? Then the system setup. So in this case, it's just atoms, no periodic boundary conditions. This is for the graphical user interface to identify what kind of bonds we have. And then at the bottom, you see the engine specifics. So for those of you who have been using ADF for a long time from the command line, this input structure is much more simple, but of course it's much different than it used to be. So whenever you take an old input file and try to run it with ADF in our 2020 release, it will try to convert it and give you a new input file. And then you should check whether that makes sense and then try to run it. If you can't find a good way to convert your older input structures, please send us a note at support@scm.com. So hopefully these were a few features that could be of interest to you. There are other features as well. So let me just point again to the release notes. And you can see here all the new features available in the central driver. So I didn't discuss external electric fields, but these are available now. You can do spectroscopic calculations such as Raman and VCD, also with DFTB and MOPAC now. And there are a number of interesting analysis properties available for trajectories. I'll point you to relevant presentations by my colleagues on that as well. Okay, so please let us know what you would like to see in our 2021 release, and let us know of any other comments and suggestions for improving our software. We'd really like to help you with your research now as well as in the future.